This work is for 2.4 GHz microwatt hour energy harvesting. Uh, Especially, we focus on the rectifying diode. So rectifying diodes have several device parameters such as parasitic resistance and capacitances. And we wanted to identify uh, which parameter is the dominant to for uh, low input power. I mean higher power efficiency at microwatt level. And here's the system we are looking at. We are assuming that the Rectenna uh, supply supplies the following sensor IC, which has very low power, such as 0.5 volt, 10 microampere. In this situation, sensor IC requires microwatt level. And so far, there are several existing work on that design for Rectenna. Fujimori and his co-workers focus on power efficiency versus RS, series resistance, and CJ, parallel capacitance, at a load condition which maximize power efficiency. In this situation, the voltage and current conditions are determined to get maximum power efficiency. That is not the case when the Rectenna derives the sensor IC, which needs a specific voltage condition. And Lawrence and his co-researchers developed tunnel diode, which is a different physics from standard Schottky barrier diode. The tunnel diode has higher power efficiency than Schottky barrier diode, and tunnel diode has lower effective potential barrier than the Schottky barrier diode. So question was which parameter determine the higher power efficiency, a lower potential barrier or lower junction capacitance. And therefore, in this study, we focus on the low power Rectenna and which device parameter determine the power efficiency, so that the device engineers can focus on that device parameter for a higher power efficiency at microwatt level at a specific voltage condition. This is the simplified RF energy harvesting system and parameter definition. Antenna, matching circuit, rectifier diode and decoupling capacitor, and load IC. Antenna is modeled by voltage source and real part array impedance, and Z-in is defined the impedance that voltage source sees. Because the rectifier diode has capacitance rather than inductance. Therefore, matching circuit is assumed to be an inductor connected in parallel in series. Rectenna diode has RS, CJ, and this symbol indicates the DC term expressed by this equation 1. Usually here VTH is the thermal voltage kT over Q. However, in this work we use this parameter as a variable parameter such as RS and CJ to think about different types of diode such as tandem diode, and also saturation current IS, and the here current components REC is the DC component given by equation 1, and AC current component by CJ, and here's IDD is total current, but here after IDD indicate average current per cycle. Equation number 2 shows the diode forward bias, because anode voltage is defined as V in diode, and output terminal voltage is now VDD. And number 3 is defined as available input power. This input power is defined by the power when the antenna is connected with array, which has the maximum output power. Under such condition, the available power is given by this equation. Because output power is given by DC voltage and DC component of current, and therefore P out is expressed by equation 4. And in this work, power efficiency eta is defined by equation 5. P out divided by P AV, average available power. And in this work, nominal parameter values are used as follows when not specified. Those both values are used. Of course, in the following graphs, x-axis shows the variable, and the other parameters are fixed as these values. And we assumed in this work the diode is the Skyworks SMS 7630, which has these device parameters. Because Schottky diode, the VTH in this case 26 millivolt at 300 Kelvin, and at 2.45 GHz the available chip inductor and chip capacitors has these kind of parameters range. And so now we are going to focus on low power regime. raw power indicate that the this diode DC component uh, turn on in a very limited time of period, uh, which means the majority of time uh, this component is off. Therefore, to the zeroth order equivalent model, uh, we extracted this portion like this. Because this is a small signal uh, circuit, the this CJ is connected to AC ground. Then this equation can be held. Z in is given by the sum of these impedances. Because here's the simple impedance chain, this input voltage and this anode voltage of core diode related with this equation, where the Q is given by this. When here this reactance component is cancelled out with equation 9. This value V in minimum is defined by this. So this is a situation where this diode starts turning on because now the output terminal voltage VDD, and we want to turn on this diode. Therefore, V in diode must be greater than VDD. So at this critical point, the input voltage must be greater than this, and which is expressed by this equation 10 using equation 7 and 8. So first we confirmed whether this equation 9 can be sufficiently okay using ADS simulation. So we swept the parameter Cj, and we identified the optimum RM, and the maximum error was 80% or less. And then we can estimate minimum input power, available input power, to make this diode starts turning on. So because we already get equation 10, and based on the definition of PAV, equation 3, then the PAV minimum is estimated by equation 11. So based on this nominal parameters, then so minimum available power is estimated to be 70 microwatt to get the VDD of zero point 0.5 volt. And this means that you must input power greater than this value, critical value. So more than this power can make the DC component, core component, step down on to get a finite output power. Next, let's look at IV curve of tunnel diode, which was provided Lorentz paper. This is voltage and current curve, and black line shows the measured data, and dotted line in red was fitted with this polynomial. You see this well fit. However, if you extend the voltage condition a little lower or a little higher, then this polynomial shows a non-physical behavior like this. So instead of using many fitting parameters, we tried to fit with this simple equation by using this VTH as a parameter. So when you input this value with 20 millivolt and IS of 1 microampere, we get this continuous line in blue, which is fit in this region. And then before moving forward, we assume that the per efficiency ether has this kind of function, which is expressed by this graph. So horizontal parameter pi is one of these four parameters. When the parasitic element increases, power efficiency must be reduced like this. There are two specific parameters, P0 and slope lambda. At this specific point, the ether degraded by 50%. Beyond that, the slope has a straight line when the y-axis is log plot. And finally, we found that this Skyworks device parameter can be hit with this specific parameters. So as you see, the lambda for CJ was 2.2, which is much greater than RS and PTH. These graphs shows details. Y-axis the ether, and its axis is the CJ, RS, PTH, and IS. There are several lines which has very big the discrepancy at a very extreme case, and so if we get rid of that data, of course that data must be has an important information, but in this presentation I focus on the nominal behavior. So lambda of 2.2 indicate this slope, and lambda equal 1.5 has this shape. And this P0 shows a 50% reduction point. And if you want to have a more specific critical point, you may want to have a lower value than these P0 values. For example, in a CJ curve, if you have the CJ of zero point 0.1 picofarad or lower, then it doesn't have any uh, effect of the CJ. I mean, even though your device parameter varies a little, say plus minus 20%, however, if your CJ is lower than 0.1 picofarad, the heat doesn't change much. Similarly, when your diode parameter RS is 10 ohm or less, then your ether doesn't have any significant variation across RS. VTH has a very different behavior, which has very small lambda, which indicate that even your the barrier height can be much lower than the nominal case. That doesn't improve your ether much. So under these results, we should focus on a lower CJ rather than reduction of VTH. For IS, a little different from the other cases. In this demonstration, if your IS is greater than, say, 10 microampere, it start to degrade because in this demonstration, our target output current was 10 microampere. Therefore, if your IS greater than 10 microampere, this diode always flow 10 microampere as an offset. So even if you transfer the power to output at a very low power input, but majority of the output power flows back to input side, and that's operation expresses this behavior at higher side of IS. If your IS was very low, and but the ether doesn't change much. Slightly, of course, there are slight reduction as the reduction in IS, because if you want the output power of the 5 microwatt, for example, and then your input voltage must be a little higher than the case where IS of higher IS. But because of the exponential behavior of voltage, whereas the IS is simply proportional, and so even with little lower IS, little higher input voltage can make your output power back to the target. This is the reason why this slope is not so significant. In this graph, probably this range is a safe one. And this graph shows a container plot of eta on CJ and VTH. The boundaries indicate eta of 10%, 20%, 30%, 40%. You see, in this direction, there is no significant variation, whereas in horizontal, vertically, the eta varies a lot, meaning eta has a significant dependency on CJ. These points indicate Schottky barrier diode, these values, and tunnel diode expressed by here. Tunnel diode was Lorentz groups. Tunnel diode has very low junction capacitance, so that's why their tunnel diode has higher power efficiency than the standard Schottky barrier diode. The reason was not the reduction in potential barrier, but the reduction in CJ. Therefore, even if your tunnel diode had much lower potential barrier than tunnel diode that Lorentz group developed, this is not so significant to improve power efficiency. This is a graph showing eta versus input power, and this is a Schottky barrier diode. This symbol shows the Schottky barrier diode generate the 5 microwatt at VDD of 0.5 volt, and in PAV of minus 15 dBm, your output reaches 5 microwatt. With TD tunnel diode, you get a 3 dB reduction at input power. Even with TD2, you just get 1 dB improvement than the TD. So in summary, we showed a simplified circuit model for microwatt energy harvesting or microwatt wireless power transfer. And in this model, we also introduced effective potential barrier of tunnel diode to discuss with the other type of tunnel diode, other type of rectifier diode. And sensitivity of device parameters investigated to get a higher power efficiency. And the conclusion was CJ was the most significant factor for higher power efficiency. So in this study, we used one demonstration. However, this approach should be able to apply another frequency range, another power output power point, and so we hope that this work could contribute to device designs and also the circuit designs for Rectenna. Thanks.